Hey everyone, in this video we're going to talk about the min-cost labeling problem. This is a more general version of the Google Christmas party problem that you're looking at in the homework. So in this problem, you have a tree and your goal is to label each node numbers 1 to 3. And you can think of this as giving different Christmas presents. So you want to give a different Christmas present for parents and children of the tree. The reason for this is if you think of it as modeling some corporate hierarchy, maybe the boss getting the same present as one of their immediate employees, they would kind of feel cheated, like you don't really respect them enough. So to make sure that everyone's happy and feels special, we're going to make sure that the label or the present any node gets is different from the labels of its children. So here, if one is the CEO of the company, we make sure all the top executives are getting 2s or 3s, that type of present, so that the CEO doesn't have a conflict. So that's the goal in the problem, is we want to pick labels 1, 2, or 3 for every single node in the graph. And we want to do this to minimize cost. So what's our cost here? Well, we incur a cost if we ever have a child gets a lower label than its parent. Then we get a cost. So in this example tree here, the nodes highlighted in red, these all incur a cost because here this child has label 2, but their parent has label 3. So you could think of this as modeling the child got a worse present than the parent, and so they're kind of jealous, and so get a cost accordingly. So in this example, there's a total of 9 different costs. So the total cost of this tree is 9 because there are 9 red highlighted nodes that will incur a cost. So now our goal overall is to pick labels for each node so that the total cost is minimized. In particular, remember the labeling, no edge, V to U. So if V to U is an edge, then the label of V has to be different from the label of U. In other words, the presents are different. Okay, so that's our problem we want to solve. As usual for these types of tree problems, we want to think about in the middle of the process, and in general for DP or recursive problems. So if we were just in the middle of the process, we're at some node V, maybe we decided labels previously of all the ancestors. And now we want to figure out what to do for V. So in particular, V might have some children, and they have their own subtrees. So what information do we need to pick the label? So there's 3 possible labels. Which one will be a good choice? Well, the choice of label that will cause us to have minimum cost overall depends on whether V gets a cost or not. Now, whether V gets a cost depends on the parents. So in particular, we have to remember the parent's label to figure out if a label for V adds cost to the overall labeling. So at the bare minimum, we need to know the parent's label so that we can accurately determine the cost of the subtrees. Now, do we have to remember anything else? It'll turn out to be no, but that's a good thing to think about. So we're in the subtree with V, we're calculating the total cost in the subtree, and we know the parent's label as well. And our goal is to decide, the decision problem we're looking at is decide a label for V. So now we can write a recursive formulation. So let's call our function ML for min labeling. And actually, let's call this P. And this is the cost of the min cost labeling for the subtree that's rooted at V. Where the parent of V has label P. So that's what we want to compute. And naturally, because we're doing dynamic programming, we're not going to overcomplicate it. So we're just going to try all possible labels. Well, all valid labels. So remember, we can't have the same label as our parent. So if we write out a recursive formulation of this problem, we'll have our min cost labeling. So actually, let me say MCL. Min cost labeling of VP. What's this going to be? It'll probably be one line, actually. So we're going to loop over all possible labels. All labels L in the set 1, 2, and 3, other than P, because we can't choose P as one of the labels. You can't have the same label as your parent. So we just try them all. And then we get a cost only if the value of L is less than P. So we're going to have an indicator here. So this will be 1 or 0, depending on whether L is less than P. So if L is less than P, then the brackets equal 1, else they equal 0. And this is called the Iverson bracket notation that we've been using. And we're going to keep using it. So we get a cost, or we don't, depending on the label that we choose in the min. And then we also have the cost for the recursive subcase. So for every child of V, V to U, we need to look at the min cost for those subtrees where their parents, all of their parents are the same V, and so we're always putting the same L here. And that's the entire algorithm. So at the very end, we just return MCL of the roots, R. And then we have two choices for the second parameter. So we can either just take a max or a min over all possible 1, 2, and 3, or we can just put a 0 there. So if we put a 0 there, then for the very first call, P will be 0. That's not even in the set, and so we're not excluding any of the possible numbers. So the choice of 0 here allows us to pick any label for the root. Okay, so that's the entire recursive formulation. It's just one line, actually. Note the base cases are built in. If you're ever at a leaf node, then this will be 0. And so like usual, the base case is built into the recursive part. Actually, let's make this 4 instead of 0. So if we made this 0, then L will always be less than P. So we always get a cost, which is not what we want. So if we put a 4 there, everything's always less than it. And so, okay, actually 0 is correct there. If we put 4 instead, this would always be true. We want L to be less than P. L less than P is the bad thing. So 0 is always less than L. So it'll always be the good part. Cool. So the algorithm's super simple in the recursive formulation. The correctness is directly from optimal substructure. So in order to get an optimal solution overall, we can just glue the optimal solutions for the children to the optimal choice for V. So that's optimal substructure, but overall the correctness is just we either make the label of V L or we don't, and we just try all possible L. So ultimately the correctness is V needs a label, and we try them all. Recursion fairy computes best labeling for all children given the choice of V's label and V's label plus the recursion fairy's labeling gives a labeling for the whole tree TV. And so choosing the best one is optimal. So really this is induction proof. This is the induction hypothesis. But for DP, we can leave it more vague and just give a slight correctness argument. Everything else is mechanical. So now let's do the DP stuff. So how many subproblems are there? Well, V can be any node. So there's O(n) of them. And then P can be anything from 1, 2, or 3. So overall, there's O(n) subproblems. Technically, there's like 3n of them. The next step is we need to pick a data structure. So the data structure, this one's a little weird because for each element of the tree, we also have many choices. So what we're going to do is either you can have 3 parameters, v.1, v.2, v.3, corresponding to each choice of label, or you could have an array at each v. Which is v.l, which is an array from 1 to 3. So either of those works. In general, if instead of like a fixed number 3, you had k of them, the array approach is probably more standard, but in this case, either is equivalent. Okay, now we have to identify our dependencies. So our data structure is the tree, so we're just going to draw a tree. So let's say this is our tree. this is node V. And we also have possible labels L from 1 to 3. So if we're at this subproblem, we need to have solved for each child, U and W, the problem for each 1 through 3. So the dependencies look like this. We need to compute their entire array for each child before computing the entire array for the parent. And so what would be a good order to do that? Well, notice the label doesn't matter. So the order of the labels we consider doesn't matter. So we can pick any order for them. All that matters is we do the children are completed before the parents. And so as per usual, we can just do a post-order traversal. And have L in any order. And that will be our evaluation order. So that's part D, evaluation order. And then what's the last step? Well, what's the running time? Well, we have O of n subproblems. And for each subproblem, we're doing constant time. So again, for these tree problems, you want to think of, for each node, how much does it contribute to the time of its parent? So for each node, you have the UL pair contributes 1 to this min. So you have the sum here, and then any U comma L appears at most once. And so, really, you're only doing a single addition for each U and L pair. So you're doing constant amount of work. A child causes constant amount of work towards each parent. And so since there's one parent per child, overall we end up with constant work per parent, O of n parents in the worst case, and so it's O of n time. Or you could even think of it as, for each edge in the tree, you do constant work. And so that's also O of n. Same idea. Since it's a tree, the number of edges is almost exactly the same as the number of nodes. As for the space, it's O of n. We just added constant space for each node in the tree. And so overall, that's the entire algorithm for computing the labelings, or for computing the optimal Christmas presents.